This video covers the transport of solutes through membranes. We will first review the electrochemical gradients and the energy that they can provide, and then we will cover the transport through membranes with the different mechanisms that govern how molecules or ions will go from one side to the other of the membrane. So first of all, let's remember that membranes play a critical role between the cell and its environment, and this role is a role of an interface. So it will first of all act as a selectively permeable barrier. So this barrier will be able to generate gradients because it will contain solutes on one side and prevent their entry or their free movement to another area of the cell. So this will be a gradient generator, and gradients are a form of energy that can easily be converted into chemical energy or kinetic energy that will help for the movement of other solutes or molecules. We will see that in the next slide, and I suggest that you read the pages from 327 to 334. Also, the membrane is a location where you will find transport systems that will selectively allow solutes in and out of the cell, and it is also the site of communication systems, so the receptors that will be able to receive extracellular signals and transmit an intracellular response, or adhesion systems that will be able to establish contacts and anchoring or adhesive structures with the extracellular matrix or other cells. So we just said that membranes generate gradients because in fact they control the flow of solutes. If the solutes cannot move freely through the membrane, then forcefully the solute will accumulate on one side and create an area of high concentration compared to another area of low concentration. And this is what we call a gradient, so areas with different concentrations of solutes. And if we want to look at an analogy, we can compare that to people accumulating or building up on one side of the door of a store the day of Boxing Day, and you will understand the gradient very easily if you understand that as soon as we open the doors of the store, then there will be a huge and massive entry of people into the store because of this strong gradient or the accumulation of a high concentration of people on one side and almost no people in the other side. So you can understand pretty easily that this can create a form of energy, because if you have so many solutes, let's say, accumulating on one side of the membrane, if you open a door or a channel or a pore through the membrane that allows the solutes to get into the cell, then, or at least in the other area where there are less of these solutes, then they can bring with them, or they can power, transduction of energy because of this flow. So this enormous difference of concentration from one side to the other can be converted into a form of energy. So it is relatively easy to calculate how much energy we can get from a concentration gradient. And in fact, if you consider a membrane enclosed compartment, so this can be a cell, this can be another compartment within a cell, at least a compartment where you have a membrane that encloses and forms two different environments. So the environment out and in the compartment, or in the membrane enclosed compartment. So everything, if you remember your chemistry courses, everything has an intrinsic form of energy that is called the Gibbs free energy, or G. And when a solute that is contained into a compartment is located inside, it has a free energy of the solute inside. The same solute that is contained outside also has energy, and it is the energy found of this solute outside. If you make the difference between the G inside and the G outside, it will give you a difference of energy, or delta G, and this delta G is the potential energy that can be released when the movement from out to inside occurs, given that there is a chemical gradient or a difference in the amount of solute out compared to in. So you can calculate the delta G with a different formula. The formula is R multiplied by T. So R is a gas constant, T is the temperature in Kelvin, ln of the concentration inside divided by the concentration outside. So you know the concentration of the solute inside, you know the concentration of the solute outside, you make the ratio, you ln the ratio, and then you multiply it by R and T. This gives you the delta G, or the difference in energy between the solute inside and the solute outside. So if delta G is negative, it means that when the movement will occur from outside to inside, it can release energy, so there will be less energy at the end of the movement than at the beginning. So the release of energy means that it will, or it can occur spontaneously as long as a door is open in the membrane and will allow the flow of solute from outside to inside. If in contrast delta G equals 0, it means that you are at equilibrium, so every movement of the solute towards the inside will be equilibrated by a movement outside, because there is an equal concentration inside and outside, so no movement occurs at all. In fact, it doesn't mean that no movement occurs, but every movement inside is equilibrated by a movement outside. So you have this, in fact, no change in the concentration. If delta G is positive, then it means that the solute inside has more energy than it had outside. So it means that you should gain energy during the movement. So this is not possible unless you provide an input of energy under a different form, but the spontaneous movement is not possible because it cannot release energy, it has to take in energy. And you cannot have more energy at the end than at the beginning unless you put energy into the movement. So a delta G, a positive delta G, will mean that the movement will not spontaneously occur from outside to inside in this situation, because it would require an input of energy. Basically, this is what happens when you go against the gradient. The delta G is positive, so it is not possible to do the movement spontaneously, but it is eventually possible to do it as long as you have something that provides energy. So usually it is a pump that will do that and catalyze ATP in order to provide this energy needed to go against the gradient. Now, this was the delta G, but the delta G doesn't only deal with the difference in concentrations that basically characterize the gradient of concentration, or the chemical gradients. Sometimes the solute also has a charge. So all what we said is true, but it is true for all the solutes that are not charged. So you can consider only their concentration gradient in the delta G. For all the solutes that are charged, or that carry a positive or a negative charge, it will modify the delta G, or the potential energy, because the charge will influence how likely the solute is to go inside or outside of the cell. Remember that the intracellular fluid is slightly negative only at the membrane level. Okay, overall the whole cell is neutral, but just at the membrane level, there is an accumulation of negative charges just under the inside leaflet of the membrane. So the intracellular fluid at this place is slightly negative, and this will provide an electric potential. So because the membrane, the inner membrane, the inner leaflet of the membrane has a slightly negative charge, it gives an electric potential to attract positively charged substances. we consider that for most cells, the membrane potential is around minus 70 millivolts, but this can be very variable. Okay, we know cells that have a membrane potential of minus 90, and there are cells that have an electric potential of minus 10. So this really depends on the cell type, but we consider that roughly the average is minus 70. This will potentially attract charges and or repel charges, and this has to be taken into account in the movement of the solute towards the inside or the outside of the cell. So when you consider the electrochemical gradient, it means that you consider not only the chemical gradient that we just saw previously, but you consider also the electrical gradient, so the influence of the charge of the solute compared to the membrane potential. So how do we calculate that? Now the delta G, when you take into account the charge, the delta G becomes the same thing for the chemical gradient, so RT ln of concentration inside divided by concentration outside. So this doesn't change. It is still the chemical component of the gradient. But to that, you will add another component that will be the electrical component, and you multiply the charge of the solute, the Faraday constant F, and the membrane potential. So we say that it is for most membrane minus 70 millivolts. So the charge of the solute, of course, if it is, let's say, a sugar that is not charged, you won't have an electrical component to the delta G, so this will not exist. If, in contrast, you have a solute like sodium or calcium, Z will represent their charge. So in the case of the sodium, it will be 1 plus, so Z is plus 1. If you consider calcium, Ca2 plus, Z is plus 2. If you consider chloride ions, then the charge is minus, it is Cl minus, so Z will be minus 1. So you simply multiply this charge with the Faraday constant and the membrane potential. This will give you the electrical component of the electrochemical gradient. Pay a good attention to the units because some of these constants are given in kilocalorie per moles, some of them are given in calorie per moles, some of them are given in millivolts. So you have to take all this into account so that you, when you calculate, you don't make unit mistakes. This is what I wanted to say about the energy that you can get from electrochemical gradients. Now just have a little review of the transport systems located in the membrane. Remember that membrane will have a very it will be extremely important for the transport of solutes into the cells, but the systems will be different depending on the nature of the solute. So we know that a lot of solutes can travel freely through the membrane, so they can cross the membrane without anything particular because of their chemical nature. So if they are, let's say, hydrophobic, they can go through the lipid bilayer very easily. If they are neutral and small enough, they will also be able to go through the membrane freely. Slightly polar molecules, as long as they are very small like water, can also kind of sneak through the membrane. However, they will most often rely on the presence of specific transport systems that we will cover later. So the travel of water through the membrane without pores is difficult but possible. However, most of the time water will be contained from on one side or the other and will be allowed to pass through the membrane by the means of specific systems. Now, all other solutes like polar organic molecules like sugars, amino acids, and stuff like that will not be able to go through the membrane because they are polar. They will need to have specific transporters that will bring them on one side or the other. Ions, same thing. They are very small, but they are charged. So because they are charged, they will be unable to go through the membrane freely. They will need to have specific areas in the mean of channels, and these channels will provide an area that is hydrophilic, and when it is open, it will create a continuous path between the outside and the inside of the cell. Proteins and other large molecules are usually too big to be able to go through the membrane. So if they are allowed into the cell, it is usually because of very specific systems like endocytosis or big pores or specific transporters. I would also like you to remember that a lot of solutes don't actually enter into the cells, but they will make a contact with the membrane by the means of receptors and undergo a cytoplasmic effect or effects into the cell that will eventually translate into gene transcription or gene expression. And this is because the membrane also has a very important function of signaling, or in fact sensing the environment and signaling into the cell what the environment is made of. So the contact with extracellular molecules will be another very important topic in this chapter that we will not cover in this video, but that we covered in class. So now let's have a look at the transmembrane transport. So it corresponds to the chapter 10.3 in your book. So there are three means of transport that we can identify. First of all, the simple diffusion, then the facilitated diffusion, and then active transport. So the simple diffusion, in fact, is what characterizes the diffusion of solutes that can move freely through the membrane. They don't need transporters. They have a chemical nature that allows them to move freely through hydrophobic substances. So we mentioned previously it is the case for small molecules that are neutral or for molecules that are hydrophobic. So they will be able to diffuse freely through the membrane, and then the rules of simple diffusion will apply. It means that they will always move from an area of high concentration to an area of low concentration, so down their concentration gradient. Facilitated diffusion is when solutes cannot move freely through the membrane. They cannot move freely through the hydrophobic substance. So there are proteins or transporters that will be located in the membrane and create areas where hydrophilic environment will be allowed. So it is, for example, holes, pores, channels that will create an opening in the membrane. So of course when they are open, because channels can be closed sometimes, so when they are open, they will create an area of hydrophilic environment. So it will create an opening between the outside and the inside, thereby allowing the substance to move freely through this hole. Okay, so in this case, once the channel or the pore is open, then the rules of simple diffusion apply only at the level of these transporters. Non-penetrating solutes will also use, for example, membrane carriers that are different types of transporters. They are transporters that, as their name indicate, carry the solute, so they will take the solute, make a physical contact with it, then change their conformation and release the solute into the cell. We'll review that more in details in the next slides. Then active transport is for non-penetrating solutes, again solutes that cannot move freely through the membrane, and they are moved against their concentration gradient, so they are moved in a direction that is not spontaneous, that will not release energy, but that in contrast will need to have an input of energy, because you go against the release of energy. In fact, you go against the gradient. You go from an area of low concentration to an area of high concentration of this solute. So this will consume energy, and the transporters that are involved in that are specifically called pumps. And this means that when they transport the substance, they will catalyze ATP hydrolysis in order to provide the energy that is needed to go against the gradient. Secondary active transport is a different type of active transport. In fact, we will review that also in a next slide. It is when the gradient of solute is established by the mean of a primary active transport, and this gradient is used by facilitated diffusion after. So let's have a look at pores and channels first. So these pores and channels are usually made of multimeric proteins, so proteins that have several subunits, exceptionally sometimes with monomeric proteins, so proteins that have only one subunit. What is a common characteristic to each of them is that they have a lot of transmembrane domains. In fact, each subunit, like shown here with the aquaporine, is a molecule made of many transmembrane domains, as you can see in the green picture, like the subunit topology just besides, that represents only the green subunit. Okay, we see it here and there as well, and it is represented like with all its transmembrane domains. So because of all these transmembrane domains, they will organize the protein into the membrane so that it will form a tube between the extracellular and the intracellular environment, and this tube will create an opening between outside and inside. It will allow hydrophilic or even water molecules in there. So in the example of water, which is moved by the mean of aquaporins, so aquaporins will create openings in the membrane like that are always open, and they are very selective for water, so no ion, no other substance can go through the aquaporine, only water molecules can, and water will be able to move and equilibrate the concentrations of solutes outside and inside by traveling through the aquaporine molecules. In fact, the likelihood of a cell to take in water or to release water will be totally dependent on the number of aquaporine molecules found in the membrane. So for example, in the kidney cells that are responsible for the reabsorption of water, there will be a lot of aquaporine molecules so that water can move very easily between the two sides of the membrane. In contrast to the pores, channels that allow ions to move into the cells or outside of the cells are open or closed. This is not the case for aquaporins that are always open, and the only regulation is the number of aquaporins that are found in the membrane. So you see that aquaporine is usually found in two subunits associated together that will create two channels. So in fact, two areas of movement always found together in the cell membranes. Now we just mentioned channels, so we said that the principle of the channel is a bit the same as the pore. However, the channel can be open or closed, which is not the case for the pore. What makes the specificity of a channel? In fact, the specificity is based on the shape and the charge of the solute that is to be moved from one side to the other. So in fact, it's represented here with a picture of this little baby, but it's exactly the way it works. In fact, if you look at the molecule, so here potassium channel that allows potassium ions to move from inside to outside, so they move towards the top here, okay, so they come from the inside of the cell and move outside. So you see that there is an area in the channel between the alpha helix here that has loops, and the loops are made of amino acids that have a lot of oxygen atoms protruding, and they are located at a distance that allows only solutes of the size of the potassium ions to go between the two loops. Okay, so if the ion is larger than potassium, it won't be able to go through the two loops, between the two loops. If it is very much smaller than the potassium ion, then what will happen is that the ion will be covered by water molecules, as any ion, and will not be able to move between the two loops because in fact the size will be too small. Now, when they move between the loops, what happens is that the potassium that is positively charged is attracted by the oxygen atoms that are slightly negatively charged, because it is polar. So oxygen attracts electrons, so the potassium that is positively charged is tempted to move towards the oxygen atoms, and it's not charged enough to create an interaction or a contact, but just an attraction. And because there are more and more oxygen atoms towards the top, then it will favor the movement of the potassium towards the top. Again, this is not a very strong interaction, so in fact it all depends on the concentration gradient. If the concentration gradient was very high outside versus small inside, it would go down into the cell. Okay, so we said that channels are open or closed. So there are three means that will control the opening of channels. Of course, when the channels are closed, they won't allow the solute to move into the channel, so they will be exactly like a membrane, a closed membrane. When the channel is open, then it creates an area where there is basically no membrane. Okay, so three means are most well known for the opening and closing of channels. Here I present the three of them. For the three of them, it is calcium that is moved from outside to inside because of its concentration gradient, because the concentration gradient is in fact, calcium is very much concentrated outside of the cells and found in very low concentration inside of the cells. So this is why the movement will always be from outside to inside. Again, if calcium was very concentrated inside, the movement would occur in the reverse direction. So first of all, ligand-gated channels. So ligand-gated channels are channels that are normally always closed, but when a specific ligand comes in, so usually it is a neurotransmitter, like for example acetylcholine, which is a neurotransmitter, it will bind with the calcium channel, physically interact with it, and modify the shape of the channel so that the channel opens a tube between, in fact, a tube in the middle of the channel so that the calcium can move in according to its concentration gradient. Keep in mind that the ligand may be extracellular or intracellular. For example, here, calcium calmodulin is a complex that can bind with several channels that will, in fact, the contact with the ligand will open the channel and allow more calcium to get into the cell. There is also a system of opening that depends on the voltage of the membrane. We saw previously that the membrane has a distribution of charges that is different inside and outside. Basically, a lot of positive charges accumulate on the outermost leaflet, on the, in fact, external leaflet, while negative charges accumulate on the internal leaflet of the membrane, thereby creating this membrane potential that is slightly negative, so around minus 70 millivolts. Now, it may happen that the membrane potential changes, and this will, in fact, you see here the charges are flipped. So instead of positive charges in the outer leaflet and negative charges in the inner leaflet, you have, in contrast, negative charges outside and positive charges inside. So this change of voltage will induce the opening of the channel and provide the or allow the entry of calcium. Finally, it is not represented here, but there are also mechanogated channels, so channels that will be sensitive to stretch or to mechanical pressure. So they will open after touch or specific pressure, let's say, for example, in the kidneys or in small blood vessels. So these channels will be sensitive to the mechanical stretching of the membrane. Again, keep in mind that the movement of ions will always occur in the direction of the concentration gradient, so down the concentration gradient and never up the concentration gradient. So the movement of ions can occur both sides, in fact in both directions. It will only depend on the direction of the concentration gradient. So now let's have a look on the passive carriers. So the passive carriers or facilitated diffusion carriers, they will allow the diffusion of ions and other and molecules, small molecules, down their concentration gradient again, but in contrast of the channels, they will never form a pore or a continuous opening between the outside and the inside like we just saw with the channel. So here is represented a channel. You see that it creates a continuous opening between the outside and the inside. In the case of carriers, it is not like that, okay? It's not the system. In contrast, you will have a physical interaction on one side of the membrane, then a change of conformation, and a release of the substance on the other side of the membrane. So you see that there is never a continuous opening between the two sides of the membrane. It is always closed, at least on one side. So this system will facilitate the diffusion of non-penetrating solutes. However, they will work, of course, according to the concentration gradient, exactly like the channels. However, in this case, they will be saturable. So, in fact, the maximal quantity of solutes that can be transported depends on the number of transporters you have and on their capacity to physically interact and then release their solute. So there is a level of saturation that can be reached depending of the number of solutes you have and the number of transporters that you have. So these molecules are called carriers because they actually carry or they actually physically interact with their solute. And this is not to be confused with channels that create an opening but don't carry anything, or pumps that also physically interact but actively process energy in order to move the substance. Here, if we have a closer look at a carrier, we see that a carrier can carry only one molecule at a time or several solutes at a time. So here, in the example that is shown here, you have two solutes moved at the same time. It is therefore called a symporter. So it imports two things at the same time. So here, protons and lactose. It means that one of the two substances can be a limiting factor because you need both a proton and a lactose to be able to change the conformation of the carrier. When the carrier is open towards the outside, it is called the outward configuration or conformation. Then when the two solutes are bound with the carrier, the change of conformation will occur and you will see the inward configuration that has a lower affinity for the solutes and therefore will release the solutes pretty easily because it's not really affine for the solutes in this situation. So there are different types of transporters like that, or carriers like that, if in fact they carry only one solute at a time. So let's say a glucose transporter, then a single solute is moved at once, and this is called a uniporter. So it can move in both outside to inside or from inside to outside direction, as long as it is down the concentration gradient, but it only moves one molecule or one ion at a time, so it is called uniporter. A symporter will transport simultaneously two solutes in the same direction. So from outside to inside or from inside to outside, again depending on the concentration gradient, but they will move in the same direction. So here you have the example with sodium and glucose that are moved towards the inside of the cell. In fact, here the sodium is going down its concentration gradient. It is a very strong concentration gradient. Glucose is going against its concentration gradient, but in fact, the transporter will use the kinetic energy of the sodium, for which the gradient is very high, in order to move the glucose against a concentration gradient that is usually not very high. You can have also symporters that will transport more than two solutes at a time. For example, here, sodium, potassium, and chloride ions that can be moved all in the same direction. Two of them can be in the direction of their concentration gradient, and one can be against. In this case, you will use the kinetic energy of one or two of the solutes to move the other one against its concentration gradient. Now, transporters can move solutes in two opposite directions. So, for example, here you see an antiporter, so this is the way we call them, transporting both sodium and calcium. However, sodium is transported down its concentration gradient from outside to inside, while calcium is moved against its concentration gradient from inside to outside. So again, the kinetic energy of sodium will be used to provide energy to move calcium against its concentration gradient. Another example here with sodium and magnesium moving in opposite direction, both of them in the direction of their concentration gradient. So an antiporter will transport simultaneously two solutes in opposite direction, and it is possible that one of these solutes moves against its concentration gradient. It doesn't consume chemical energy, but it will use the kinetic energy or the energy of movement provided by one of the solutes. Pumps are the word that we use to qualify active transporters that can catalyze ATP in order to move substances against their gradient. So the example here is given with the sodium-potassium pump or sodium-potassium ATPase. We call it like that because it can catalyze ATP to get energy. So you see that the concentration gradient of sodium is from outside to inside, while the concentration gradient of potassium is in contrast from inside to outside. So they should normally move with the sodium going toward the inside of the cell and the potassium going towards the outside of the cell. However, this pump will do the exact contrary, so it will move potassium into the cell and move sodium outside of the cell. So because the two solutes will move against their concentration gradient, it will require that an input of energy is given by something else. In this case, it is by the means of ATP hydrolysis. So this type of pump will consume energy, and this is because the delta G is positive, so it means that you have more energy at the end of the movement than at the beginning, so it is impossible without the use of energy or the input of energy from ATP. So the primary active transport is exactly what we see here. So you consume energy in order to move two substances against their concentration gradient. In the case of the sodium-potassium ATPase, it is always 2 potassium moved in for 3 sodium moved out by the mean of ATP consumption. Now, a lot of transports also require secondary active transport, and in fact, it is a mean of transport that in which a primary transporter will build a gradient, and then a secondary transporter will use the gradient that has been built by the primary active transporter in order to move a solute against its concentration gradient. So we saw previously that sodium and glucose can be moved by the mean of a passive transporter, so a transporter that doesn't consume energy in itself, but it will use the strong sodium gradient to move glucose against its concentration gradient. Basically, because there is a buildup of sodium outside, the transporter will move sodium down its concentration gradient and use the kinetic energy of sodium to move glucose against its concentration gradient. However, if you do that all the time, you will soon have an accumulation of sodium inside. So you need to have something else that removes the sodium from inside so that you can keep a strong gradient. So the sodium-potassium pump here will consume energy to move sodium back outside so that you keep the strong concentration gradient that allows the sodium glucose symporter to move glucose against its gradient just using the kinetic energy of sodium and not consuming ATP. So you see here in this example, a secondary active transport requires that a primary active pump will establish a gradient and keep a gradient so that a strong gradient can be used to move another substance passively against its concentration gradient. If we make a summary of several transport means, we can integrate all that in the transport of glucose at the level of intestinal cells. So you see here on the slide, if we start from the top, when you eat, there is an accumulation of glucose in the lumen of the small intestine, and the glucose transporter that is located in the brush border of your intestinal cells will move glucose from the lumen, so from the foodstuff, to the inside of the cell. However, it will do that pretty actively, but the problem is that glucose will soon accumulate into the cell. So you will soon have a gradient that will start to equilibrate from outside to inside, and even you will have a stronger gradient, in fact a higher concentration inside compared to outside. So the glucose will soon have to go against its gradient because it will constantly enter into the cell, so soon you will have a higher concentration inside than outside. How can you do to go on moving the glucose into the cell? You will use the sodium glucose symporter and in fact use the kinetic energy of sodium that is highly concentrated outside in order to move the glucose inside. So basically you use the kinetic energy of sodium to move glucose against its concentration gradient. Now, same thing occurs. Sodium will move inside, therefore you will eventually have an accumulation of sodium inside. If you don't remove the sodium, you will have an equilibration of the gradient of sodium, and the transport of glucose will not go on and will not, you will stop having glucose entering into the cell. So you need to get rid of this sodium pretty quickly. This will be achieved by the mean of the pump that consumes ATP and moves sodium back outside so that you keep the strong gradient of sodium and keep on moving glucose into the cell, absorbing the foodstuff into the intestinal cell. Now, this will create a gradient that will allow the transport of glucose outside of the cell at the bottom of the cell, basically towards the bloodstream, in fact towards the extracellular fluid and the blood vessels that are located below the intestinal cells. So because of the strong gradient that is established, like high concentration of glucose inside, low concentration of glucose outside, glucose will be moved passively because of the glucose carrier um, from into the cell to outside of the cell. It will diffuse in the leaky blood vessels that are located outside. So in fact there is no need for a transporter here, because the capillaries are very we call them fenestrated, so they have openings, they are leaky, so glucose can readily diffuse into the bloodstream. And again, the high concentration gradient from the extracellular fluid to the inside of the cell will allow the movement of glucose into the target cells. The only thing that remains to be done is to get rid of the potassium that is constantly moved inside of the cell of the intestinal cell because of the sodium potassium pump. And if you have too much accumulation of sodium inside, then what will happen is that a leaky channel will basically take the potassium and move it back extracellularly, so that you can dissipate the accumulation of potassium, the over accumulation of potassium inside. And this leaky channel will dissipate the over accumulation of potassium into the intestinal cell. This is all I wanted to say about the transport of substances from inside to outside of the cell, or from outside to inside of the cell. These are only several examples of the transport systems, but keep in mind that they usually work together in order to establish gradients and provide kinetic or chemical energy that will move substance from one side to the other.